Germany had the blueprints for Britain's best engine. They had captured examples. They had engineers good enough to reverse engineer a Soviet tank, develop the world's first operational jet aircraft, and produce a direct fuel injection system that was genuinely ahead of anything in the Allied inventory. When German technical teams examined the Rolls-Royce Merlin, measured it, analysed it, ran their tests, they understood every visible part, every bore diameter, every valve angle, every gear ratio. The copy never came. Not because Germany tried and failed, because Germany's engineers looked at the problem clearly enough to know that a copy wasn't the point. The secret wasn't inside the engine. It wasn't in any single component. It was in the fuel refinery in Pennsylvania, the controlled humidity assembly floor in Detroit, the test culture at Derby, the metallurgical supply chain that stretched from British smelters to a small aluminium alloy known as RR50, and thousands of production decisions that were never written into any blueprint at all. This is the story of why blueprints aren't enough. And the proof isn't the engine that Germany couldn't build. The proof is the engine that America could. Once America reproduced not just the drawing, but everything the drawing assumed. Picture the Erprobungsstelle Rechlin in the summer of 1940. Germany's Central Aviation Evaluation Centre on a lake in Mecklenburg, about 90 miles north of Berlin. It's a serious place. Wind tunnels, test benches, calibrated instruments, engineers with doctorates and years of production experience. When a British aircraft came down on occupied territory and was recovered in reasonable condition, it eventually made its way here. Damaged Hurricanes from the French campaign. Spitfires that had gone down over the Channel coast and been retrieved before they sank. Germany's technical intelligence operation wasn't casual. It was methodical. A Merlin, when you strip it, is an arresting piece of machinery. The two banks of 6 cylinders angle away from each other at 60 degrees, forming a tight V. The supercharger housing sits at the rear, compact and dense, driven off the crankshaft through a gear train. The valve covers come off cleanly. 2 inlet valves, 2 exhaust valves per cylinder. The exhaust valves noticeably heavier, their stems sealed. The crankshaft, when you can get to it, is a single forged piece, 7 bearings machined from material that has been nitrogen hardened after forming. The lead-bronze bearing shells, when you hold them, have a particular quality to their surface finish. Not rough, not glossy, but consistent in a way that speaks to controlled manufacturing rather than handwork. German aviation researchers at the Deutsche Versuchsanstalt für Luftfahrt had conducted technical analysis on at least one Merlin variant, with their findings documented in abstracts later reviewed by the British Ministry of Aircraft Production. A 1945 SAE paper, prepared as a German assessment of Allied engine technology, shows that German engineers had examined Merlin alloys in direct comparison to their own. They recorded a precise observation. At high temperatures, the Rolls-Royce alloy was superior. Not marginally, specifically and measurably superior in the conditions that mattered most. Sustained high-power operation at combat temperatures. So they knew what they were looking at. In 1944, Germany went further. They fitted a captured Spitfire Mark V with a Daimler-Benz DB605 engine and sent the result to Rechlin, not to copy the Merlin, but to understand the Spitfire's radiator installation and airframe aerodynamics. The DB605-powered Spitfire was found to be 15 miles per hour faster than the original at low level, which told the engineers something useful about the airframe's drag characteristics and cooling system. The only documented 1941 discussion about fitting a captured Merlin to a German airframe was correspondence between Messerschmitt and Daimler-Benz, and the purpose stated in that correspondence was radiator positioning, not engine replication. There is no known instance across the entire war of Germany running an active program to copy the Rolls-Royce Merlin or Griffon. That isn't a story of German incompetence. It's a story of German engineers being precise enough to recognize that copying the drawings wasn't the problem. And if that conclusion seems counterintuitive, it becomes considerably less so once you understand what the Merlin actually was and what it took to make it work. Most people, if they know anything about the Merlin, carry one of four explanations for why it mattered. The first is horsepower. It was more powerful than anything Germany had, full stop. The second is the supercharger. Britain cracked two-stage supercharging while Germany was still on single-stage designs. The third is fuel. The RAF was running on 100 octane when Germany was stuck on 87. The fourth is national genius. Rolls-Royce simply had better engineers. Each of these contains something true. None of them explains the engine. On horsepower, the Daimler-Benz DB605A with methanol water injection could produce around 1,800 PS in emergency rating, comparable on paper to the Merlin 70's 1,710 horsepower. Late-war German engines approached Merlin power figures. The raw number was never the whole story. On the supercharger, accurate but incomplete, Germany eventually developed two-stage supercharging. The UMO 213E, which entered service on the Focke-Wulf FW190D9, used a three-speed, two-stage supercharger. It was 2 years behind the Merlin 61 and arrived in far smaller numbers, but the technology wasn't beyond German engineering. The question is why it arrived so late and in such constrained quantities, not whether it was theoretically possible. On fuel, here is the one that genuinely surprises people. Britain entered the war running its frontline fighters on 87-octane aviation Spirit. Germany already had 100 octane. Britain had to buy its high-octane supply from America. The first tanker load arrived in June 1939, before the war had even begun. So the story of fuel is more complicated than Britain had better petrol, and getting that story right is essential to understanding what the Merlin actually did with its fuel, and why Germany's engines couldn't do the same. On national genius, the Packard motorcar company disproves this one entirely. American engineers at a car factory in Detroit reproduced the Merlin successfully. If the engine required British ingenuity as its essential ingredient, it shouldn't have worked when built by machinists in Michigan. The fact that it worked, not just adequately, but at or above Rolls-Royce's own production standards in consistency, tells you the genius was never national. It was systemic. So the full explanation isn't the supercharger alone, not the fuel alone, not the metallurgy alone. It was all of them simultaneously, held together by a production culture that accumulated thousands of incremental improvements across 9 years of development. Cyril Lovesey, who led Merlin development at Rolls-Royce, described the engine's wartime progress as achieving closer manufacturing tolerances and lower safety factors. The engine got better by being made more precisely, not by being redesigned from scratch. The Merlin's displacement never changed. It remained 27 litres, 1,650 cubic inches, from first run on October 15, 1933, to the end of production in 1950. All the power growth came from learning to make the same engine better. That is the story the blueprints couldn't tell. Start with the supercharger, because this is where the gap was most dramatically visible and where Germany eventually caught up, but at enormous cost in time. A supercharger exists to solve a physics problem. Air gets thinner with altitude. A naturally aspirated engine loses power as it climbs because there is progressively less oxygen entering the cylinders on each stroke. A supercharger is a mechanically driven compressor that forces additional air into the engine, maintaining power at altitudes where it would otherwise fall away. The higher you can sustain effective boost pressure, the higher your aircraft can operate at useful combat power. In the mid-war period, fighting over Britain and the Channel happened at 20,000 feet and above. The engine that could sustain power at those altitudes dictated the terms of the engagement. The early Merlin, the Merlin II and III that fought in Spitfires and Hurricanes during the summer of 1940, used a single-stage, single-speed supercharger. At sea level, the engine produced around 1,030 horsepower. Performance held reasonably well at medium altitude. Above 15,000 feet, it began to tail off. Stanley Hooker arrived at Rolls-Royce in 1938. He was 31 years old. He had a doctorate in mathematics from Oxford and had spent his career since then as an applied mathematician, working on fluid dynamics problems that bore no particular relationship to aviation. He had no prior experience with aero engines whatsoever. His supervisor, J.E. Elor, who had come to Rolls-Royce from the Royal Aircraft Factory and whose speciality was superchargers, handed him the technical documentation for the existing Merlin supercharger and, in effect, asked him to read it and see what he thought. What Hooker found when he worked through the aerodynamics was that the existing design was leaving significant efficiency on the table. The air intake duct wasn't optimally shaped for the flow conditions it was handling. The impeller blades weren't profiled to extract maximum work from the air they were compressing. The diffuser, the component that takes the high-velocity air coming off the impeller and slows it down to increase pressure, was losing energy in the transition. These weren't catastrophic failures. The engine was working. But Hooker's mathematics told him how much better it could work, and the gap between actual and theoretical was meaningful. He set about redesigning all three components. The intake duct first, reshaping the entry geometry to reduce turbulence and improve the uniformity of flow reaching the impeller. Then the impeller itself, reworking the blade profiles. Then the diffuser. These weren't rough-and-ready modifications. Each change required the mathematics to be right, then the machined component to match the mathematics, then the bench test to confirm the component matched the prediction. Hooker described this process in his autobiography, Not Much of an Engineer, in terms that make clear the work was iterative and genuinely difficult. This wasn't a case of a clever man instantly solving a problem that had stumped everyone else. His early work raised supercharger efficiency from 68% to 76%, 8 percentage points. In absolute terms, that meant the supercharger was delivering substantially more compressed air to the engine for the same mechanical input. Within months of starting at Rolls-Royce, Hooker had added approximately 30% more power to the Merlin. The same block, the same pistons, the same crankshaft, a different supercharger. His cumulative work culminated in the Merlin 60 series, conceived in response to a Ministry of Aircraft production request in March 1940, for an engine capable of operating effectively at 40,000 feet. Hooker's solution was to place two supercharger stages in series, the output of the first stage feeding the input of the second, with intercooling between them. The two-stage engine bench-tested in April 1941. Two-stage supercharging isn't simply more supercharger. The second stage compresses air that is already compressed. The charge entering the engine is extremely dense and extremely hot. Heat is the enemy of detonation margin. Hot air ignites prematurely, destroying the power advantage you compressed twice to create. Managing that heat requires an intercooler between the stages, a second cooler, the aftercooler, between the second stage and the cylinders, and a coolant circuit entirely separate from the main engine cooling system, running at up to 36 gallons per minute through the wheelcase housing. Without the intercooler, Hooker estimated the charge temperature would reach 400 degrees Fahrenheit before it entered the combustion chamber. With it, the temperature dropped to manageable levels. In Hooker's estimation, adding fuel ahead of the supercharger reduced the air temperature by around 25 degrees Celsius, and that margin was what prevented detonation at the boost pressures the system was now delivering. The whole assembly must manage heat, pressure, and gear ratios across the full altitude range. None of that integration is visible from external inspection of the engine block, and none of it was obvious from the drawings. What the drawings showed was the geometry. What they couldn't show was the 10 years of development logic that determined why the geometry was exactly what it was. The Merlin 61, the first production two-stage variant, entered operational service on the Spitfire in 1942. It raised that aircraft's operational ceiling from 30,000 to 40,000 feet. It added 70 miles per hour to the Spitfire's top speed. At 30,000 feet, the Merlin 60 series gained 300 horsepower compared to the single-stage Merlin 45 it replaced. The Packard-built version of this engine could develop over 1,270 horsepower above 30,000 feet, an altitude where any single-stage engine was producing a fraction of its sea-level output. Germany's production engines used a different philosophy for variable speed supercharging, a hydraulic coupling that varied supercharger speed continuously rather than through fixed gear ratios. This was a genuine engineering solution to altitude performance, different from Britain's approach, but not theoretically inferior. Germany's challenge wasn't that the idea of two-stage supercharging was impossible to imagine. The UMO 213E proved the concept was reachable. The challenge was that the Merlin 61 arrived in squadron service in 1942, and the UMO 213E arrived operationally in 1944. 24 months during which Allied aircraft had access to altitudes that German single-stage engines couldn't profitably contest. By the time Germany had a comparable altitude solution, the war had already moved. The fuel story requires more precision than it usually gets because the popular version is backwards. Britain entered the war running its frontline fighters on 87-octane aviation Spirit. Germany's fighter engines were running on C3 fuel, approximately 94 to 96 octane, improving throughout the war. German bombers and transport aircraft used B4, a lower-grade standard fuel. So, on the face of it, at the outset, Germany had the fuel advantage. Octane rating is a measure of a fuel's resistance to pre-ignition, its ability to be compressed without detonating before the spark fires. Higher octane doesn't contain more energy. It allows you to compress the fuel-air charge more aggressively before it ignites, which means more force per stroke, which means more power from the same displacement. In a supercharged engine, octane rating determines how much boost pressure you can safely apply. More boost equals more charge density equals more power. The ceiling is set by the chemistry of the fuel. The Merlin on 87 octane was rated for a maximum boost of plus 6.25 pounds per square inch. The RAF decision to acquire 100-octane fuel was taken in March 1939. The first tanker load arrived in Britain in June 1939, stockpiled before the war began. The modification required to exploit the higher octane was physical. Shrouded cylinder heads fitted to the engines to withstand the increased cylinder pressure. Formal approval for the plus 12-pound boost setting came in March 1940. By June 1940, before a single Battle of Britain sortie had been flown, every frontline Hurricane and Spitfire in fighter command had converted. The Merlin III on standard 87 octane produced around 1,030 horsepower. The same engine on 100 octane at plus 12 pounds boost produced approximately 1,310 horsepower at 9,000 feet. Same block, same displacement, same mechanical design. Around 135 additional horsepower because the fuel permitted the throttle to open further before detonation intervened. Air Chief Marshal Arthur Tedder, summarising the Battle of Britain's outcome afterward, placed three factors at its centre: the skill and bravery of the pilots, the Rolls-Royce Merlin engine, and the availability of suitable fuel. Fuel was the third item on his list, not an afterthought. The pilot accounts from those weeks are worth reading closely because they illustrate the effect more directly than any power chart. On the 19th of May 1940, weeks before the Battle of Britain formally began, a flight lieutenant of 87 Squadron noted what happened when he pulled his Hurricane's boost control over France. The gauge climbed to 12 pounds and speed jumped by around 30 miles per hour. A week later, a pilot officer of 151 Squadron recorded pulling the plug and climbing at 10 pounds boost. Another combat report from the same period records the same action. Full 12-pound boost, the throttle pulled past its usual limit, and the pilot overtook the enemy aircraft rapidly. These aren't abstracts from an engineering paper. They are working pilots recording in real time the performance difference that fuel chemistry made. German pilots who had fought the RAF over France and then encountered the same aircraft types in August 1940 were genuinely confused. The planes appeared to have changed. A Luftwaffe pilot who had bounced a Hurricane successfully in May found a Hurricane in September was a different proposition in a climb or a chase. He had not been misinformed about what he was fighting. He simply didn't know what was in the fuel tanks. The secret stayed secret until a Spitfire went down in occupied Belgium, and German technicians swarmed over the wreck. They tested the fuel remaining in the tanks and found Britain wasn't running 87 octane. Their further finding was that their own best fighter, the Messerschmitt 109E, couldn't exploit it even if they obtained it. The engine's supercharger wasn't calibrated to use the higher boost the fuel would permit. That is the structural point the fuel story makes. Germany had C3 at 94 to 96 octane. But the DB605's technical documentation shows it was designed fundamentally around B4 fuel, with later adaptations for C3. The boost margins, the supercharger gearing, the cylinder design, none of it was calibrated around the same exploitation of high-octane chemistry that the modified Merlin had been since March 1940. You can run a higher octane fuel in an engine that wasn't designed to exploit it. You don't necessarily get proportionally more power. The fuel and the engine have to be designed as a system, with the boost architecture and supercharger tuning specifically matched to what the fuel chemistry permits. The United States produced 100 octane through the Houdry catalytic cracking process, developed by the French engineer Eugène Houdry, working for the Sun Oil Company. Production scaled from 40,000 gallons per month at the start of the war to 400,000 gallons per month by 1944, drawn from 77 separate plants across America. Germany had no equivalent process and no equivalent supply chain. One wartime analysis concluded that a difference of only 13 octane numbers made possible the defeat of the Luftwaffe in 1940. Germany never produced 100 octane aviation fuel domestically, not during the war, not until after it ended. This is the part nobody films. No director puts it in a war movie. There are no dramatic scenes of a factory floor in Derby where a man with a micrometer measures a crankshaft bearing to a tolerance of a few thousandths of an inch and decides whether to pass it or scrap it. But this is where the Merlin lived or died at sustained high power, and it's the clearest illustration of why blueprints couldn't reproduce the engine. The basic component list tells you something about the engineering ambition involved. The crankshaft was machined from a single nitrogen-hardened nickel-chrome molybdenum steel forging. One piece, 7 main bearings, dynamically balanced, generating torque from 12 cylinders firing in a controlled sequence at up to 3,000 revolutions per minute. The main bearing shells were mild steel housings lined with lead-bronze alloy. Rolls-Royce's documented production practice was to scrap lead-bronze bearings that failed specification, rather than attempt rework. The cost of a bearing that fails at combat power is an engine, and potentially an aircraft and its crew. The cylinder liners were high-carbon steel set in 2-piece cylinder blocks cast from an aluminium alloy designated RR50. The pistons were machined from RR59 alloy forgings. The connecting rods were nickel-steel H-section, carrying forked and plain rod pairs on each crankpin, with the forked rod housing steel-backed lead-bronze alloy bearing shells. The exhaust valves are where the metallurgy becomes most demanding. Each exhaust valve was made from KE965 steel, a high chromium, high nickel, heat-resistant alloy, with a stem that was hollow and partially filled with sodium. The sodium was encapsulated, sealed inside the stem. Its purpose was to carry heat away from the valve head during operation. As the valve opens and closes at several thousand cycles per minute, the sodium liquefies from the combustion heat and sloshes from head to stem, conducting thermal energy toward the valve guide and away from the hottest point. The valve head received a separate coating of bright ray, a nickel-chromium alloy, for additional heat resistance at the face. Getting sodium into a valve stem without contaminating the sodium, without leaving voids, without creating a seal that fails at operating temperature, requires precision manufacturing that is entirely invisible in the specification. The drawing tells you the valve has a sodium-cooled stem. It does not tell you how to reliably produce one. What happens when this precision lapses isn't a gradual degradation. At high sustained power, a bearing running on slightly off-specification material overheats, loses its oil film, and seizes, catastrophically and rapidly. An exhaust valve with inadequate heat dissipation cracks or burns through. A crankshaft machined from material with the wrong alloy composition develops fatigue cracks under the cyclic loading of combat power. These failures aren't theoretical. They are the reason Rolls-Royce ran engines off the production line continuously at full power until they failed, then stripped them down to find what gave out first. After 2 years of this, roughly 1936 to 1938, The Merlin had matured from a chronically unreliable development engine into one that could sustain 8-hour Lancaster bombing missions without attention. Germany's own technical examiners, in their 1945 assessment of Allied engine materials, recorded that the Rolls-Royce alloys were specifically superior at high temperatures compared to German equivalents. That finding didn't emerge from ignorance of what the materials were. German metallurgy was sophisticated. The assessment emerged from the inability to match what those materials did under sustained thermal loading. Germany's structural position on materials predated the war. Between 1935 and 1939, German construction steel had its nickel content reduced by 80% as strategic rationing cut into reserves. Chromium was reduced by 31%, molybdenum by 31%. These are exactly the elements that matter for high-temperature engine alloys. Nickel and chromium for heat resistance, molybdenum for strength at elevated temperatures. A 1941 analysis put it plainly: Germany's metallurgical skill couldn't remedy the deficiency in ferroalloys. German engineers found substitutions, but substitution carries performance costs precisely in the components, exhaust valves, bearings, cylinder liners that fail first when things go wrong at combat power. At Packard, the tolerance story takes an unexpected turn. When Rolls-Royce engineers received the first Packard-built Merlin and stripped it down, they were surprised. Not because the American engine was crude or inferior, but because the production line tolerance consistency was better than their own hand-fitted engines. Rolls-Royce had built Merlins the way craftsmen built high-performance machinery, hand-fitting each component, fettling surfaces individually, accepting that no two engines from the same batch were quite identical. Packard's approach, automotive mass production discipline, standardized tolerances rather than hand-fitting, produced engines that were more consistent unit to unit. The Packard assembly floor was temperature and humidity controlled to maintain clearance specifications at 0.0002 inches, 2/10,000ths of an inch. Because at that precision, the ambient temperature of the room affects the result. This is what blueprints can't convey: the organizational decision to build a climate-controlled factory for aircraft engine assembly. The quality culture that scraps rather than reworks an out-of-specification bearing. The supplier relationships that ensure the material arriving at the factory door matches what the drawing demands. The test facility adjacent to the production line, where every single engine runs before it leaves the building. Germany had capable engineers. What Germany didn't have, at the right place at the right time, was the industrial ecosystem that made these disciplines routine. On September 3, 1940, the first anniversary of the day Britain declared war on Germany, Rolls-Royce and the Packard Motor Car Company of Detroit signed a licensing agreement worth $130 million. The initial order was for 6,000 engines, later expanded to 9,000. Britain agreed to fund the necessary new plant and to provide the machine tools. Packard assigned over 200 engineers and draftsmen to the project the same week. What arrived at Packard's facilities in Detroit wasn't simply a box of drawings. The scale of documentation required to build a 27-litre V12 aero engine to military specification is substantial. Hundreds of drawings covering every component, assembly and sub-assembly, each with tolerances, material specifications, heat treatment requirements, and surface finish grades. The first thing Packard's engineers discovered when they began working through the drawings was that they were unusable as received. Rolls-Royce worked in British third-angle projection, the drawing convention standard in Britain. American machine shops used first-angle projection. The two conventions place the views on different sides of the object being described, and a machinist trained in one convention reading a drawing made in the other is liable to produce a mirror image component. Every single drawing, hundreds of thousands of dimensions, had to be redrawn before a Detroit machinist could act on it. That alone occupied a large portion of the 200-plus engineering staff for months. The thread problem came next. The Merlin used British thread standards throughout: Whitworth, British Standard Fine, British Association, for its fasteners. These aren't interchangeable with American national threads. American machine shops didn't stock them. American equipment wasn't generally set up to cut them. Jesse Vincent, Packard's engineering lead on the project, had to work out how to source or manufacture thousands of non-standard fasteners for every engine. Some suppliers had to be found who could produce British standard threads. Others required new tooling. None of this was in the drawings. The drawings specified the thread designation. They said nothing about the supplier ecosystem that would need to exist before the threads could be procured. You could read every drawing for the Merlin cover to cover and not discover that you'd need to rebuild part of your fastener supply chain before you could bolt the engine together. Before Packard, there was Ford. The Ford Company at Detroit had already received a complete set of Merlin plans and had been working on tooling before the contract moved to Packard. Lord Beaverbrook, Britain's Minister of Aircraft Production, approached Packard after Ford declined to take on the broader manufacturing commitment. The fact that Ford, one of the largest and most capable precision manufacturing operations in the world, already in possession of the drawings, didn't produce the Merlin at scale is its own data point. The drawings existed. The drawings weren't the limiting factor. Packard built Building Number 22 specifically for the Merlin production line and constructed an adjacent facility for run-in testing. A separate building where every completed engine would be mounted on a test stand and run under load before it was accepted and shipped. The run-in facility wasn't an optional extra. It was a structural requirement of quality control. An engine that passes dimensional inspection during assembly can still fail at operating temperature from material deficiencies, oil system problems, or clearance issues that only manifest under load. The only way to find out before the engine goes into an aircraft is to run it. Packard built the infrastructure to run every one. The first Packard-built engine, the V16501, ran on test stands in Detroit in August 1941. That was 11 months after the contract was signed. 11 months from signature to a working engine with full British government funding, machine tools provided, drawings redrawn, facilities purpose-built, and Rolls-Royce's technical collaboration throughout. Packard didn't just copy. Where they could improve the manufacturing process, they did. They implemented a two-piece cylinder block design before Rolls-Royce had managed to introduce it in production. The design had originated with Rolls-Royce engineers, but Packard's production environment got it onto the line first. Packard modified the bearing design, changing from copper-lead to silver-lead alloy with indium plating, a General Motors Pontiac division technique originally developed to prevent corrosion from contemporary lubricating oils. British engineers assigned to Packard were reportedly startled by the suggestion. The modification looked like a departure from established practice. And departure from established practice in precision aero engine manufacturing isn't to be taken lightly. But tear-down inspections on rigorously tested engines demonstrated that the modification was a genuine improvement in break-in characteristics and load-carrying capacity. Rolls-Royce subsequently adopted it. The technology transfer ran in both directions. The rejection rate on Packard's production line fell below 2%, comparable to or better than some British production runs. When North American Aviation tested the Packard V1650-3 in modified XP-51B airframes, the Army Air Corps moved fast. It limited P-51A production to 310 aircraft and shifted full production to the P-51B with the Packard Merlin. That decision was swift because the engine met the standard, not because anyone was being generous with a wartime Allies product. By the end of the war, Packard had built approximately 54,700 V1650 engines, roughly 37% of total Allied Merlin production. The same design that had first run at Derby in 1933. Built to the same specification, by machinists in Michigan who had 11 months earlier been building luxury motorcars. If the Merlin's secret had been in the blueprints, Ford would have found it before Packard started. If it had been national genius, America shouldn't have been able to reproduce it at all. What the Packard story demonstrates with unusual precision is exactly what the secret was. The industrial process that made the blueprint real. Every element of that process, the controlled environment, the material standards, the test discipline, the supplier relationships, had to be reproduced, not just the document that described the outcome. None of this should be taken as a verdict that German engineering was inferior. The evidence doesn't support that conclusion, and the evidence is worth stating plainly. Germany flew the world's first turbojet aircraft on August 27, 1939, when a Heinkel HE-178, powered by Hans von Ohain's engine, left the ground near Rostock. Germany put the first jet fighter into combat in 1944. The UMO-004 turbojet that powered the Messerschmitt 262 was produced in quantity, over 8,000 units, under conditions that included Allied bombing, dispersed manufacturing, and chronic material shortages. German engineers developed direct fuel injection for aircraft engines before Britain did, and it had a real tactical consequence in 1940. A Messerschmitt pilot could push the nose down into a negative G dive, and the DB601 kept running, while the same maneuver caused the Merlin's float chamber carburetor to starve of fuel and cut out. RAF pilots learned to half-roll before diving to pursue a German aircraft. It was an effective tactic for German pilots, and it worked because the German fuel injection system was genuinely more sophisticated in this specific respect. Beatrice Schilling, an engineer at the Royal Aircraft Establishment, solved the carburetor cutout problem with a small disc fitted inside the float chamber, restricting fuel flow enough to prevent complete starvation in a dive. Pilots called it Miss Schilling's orifice. It was a workaround. The full fix was the Bendix-Stromberg negative G carburetor, which Packard's American-built Merlins used from the start. Germany's fuel injection was a genuine engineering lead, and it took Britain time to match it. The UMO-213E, when it entered service in late 1944, was serious engineering. 3-speed, 2-stage supercharger, methanol water injection for emergency power. The development trajectory from the UMO-211 through the 213 represents sustained, sophisticated work. At 33,000 feet, the UMO-213 was generating roughly 1,300 horsepower. Against the Merlin 66's output at comparable altitude, Germany had closed a meaningful portion of the gap by 1944. The problem was chronology, not capability. Germany reached near parity on altitude supercharging 2 years after the Merlin 61 had already changed the terms of the air war. Those 2 years, 1942 and 1943, were the period in which Allied aircraft repeatedly operated at altitudes German fighters couldn't effectively contest, which shaped strategic bombing operations, interception patterns, and pilot attrition in ways that couldn't be undone when the UMO 213E finally appeared. The structural constraints that produced this delay were systemic and predated the war. By 1939, Germany was running multiple simultaneous high-performance aero engine development programs across 3 major manufacturers: Daimler-Benz, Junkers, and BMW. The Reichsluftministerium funded these competing programs rather than consolidating around the most promising design. The UMO 222, a 24-cylinder engine rated at 2,500 horsepower, was cancelled in December 1941 after years of development. The resources that had gone into it were redirected, but the effort was lost. By 1943 and 1944, RLM priorities increasingly shifted toward jet programs, which was arguably a correct long-term judgment, but diverted engineering resources from the piston engine programs that were actually deciding air battles in the immediate term. The strategic material position made everything harder. Nickel reserves at 20% of pre-substitution levels before the war had even started. Chromium down by nearly a third. No domestic 100-octane production capacity. The DB605's lubrication issues and fuel system deficiencies were documented during the war, not failures of design intent, but symptoms of a manufacturing system under progressive strain. Allied bombing from 1943 forced Daimler-Benz to disperse production increasingly widely, which maintained output but complicated the consistency that precision manufacturing requires. An improvised facility producing components under dispersal conditions is harder to control than a purpose-built plant with established quality protocols. Germany's engineers understood what the Merlin was. Their own technical papers document that understanding with precision. What they didn't have, and what couldn't be assembled from captured examples, intelligence analysis, or engineering talent alone, was the accumulated industrial capability that made those design parameters achievable in consistent production at scale. The Packard story closes the argument because it's designed as a controlled experiment. If the Merlin superiority had been embedded in the blueprints, in some design secret documented only at Rolls-Royce, then transferring the blueprints to America should have been sufficient, and the transfer should have been quick. 11 months and $130 million just to reach a working engine on a test stand, with machine tools provided, facilities purpose-built, drawings entirely redrawn, and ongoing technical collaboration, isn't quick. It's the minimum time required to reproduce an industrial ecosystem from scratch, even with every possible advantage. If the superiority had been national genius, something inherent to British engineering culture, then America shouldn't have been able to reproduce it. America did reproduce it, to a higher production consistency than the originator. The genius wasn't national. What the experiment shows is that the variable was the process. Britain didn't share the blueprints with Packard. Britain shared the blueprints, the machine tools, the funding for the factory, the technical personnel, the material standards, and 11 months of continuous collaboration. That isn't a blueprint transfer. That is an ecosystem transfer. And it still took 11 months before the first engine ran. Germany never failed to read the blueprints. German engineers read them and understood what they described. What Germany never had was the factory. Not the building, the entire accumulated industrial system. The alloy supply chains, the precision production culture, the fuel chemistry, the test infrastructure, the manufacturing philosophy that turned a drawing of a sodium-cooled exhaust valve into a sodium-cooled exhaust valve that wouldn't fail at war emergency power after 300 hours of sustained use. The Merlin's displacement was 27 litres from first run to last production unit. The power available from that displacement grew from 740 horsepower in the prototype stage to over 1,700 horsepower in the Merlin 66 and beyond 2,000 horsepower in the Merlin 130 series. None of that growth required a new engine. All of it required a better industrial system. Each improvement, supercharger geometry, fuel octane, charge temperature, bearing material, valve cooling, was inseparable from the others, because the engine operated as a system and the limits were always interactive. You couldn't raise the boost pressure without the fuel chemistry that prevented detonation. You couldn't raise the temperature without the metallurgy that survived it. You couldn't manufacture consistent metallurgy without the alloy supply chain that delivered consistent material. You couldn't exploit any of it without the test culture that discovered what failed and corrected it before engines left the building. None of that is a secret. All of it's the kind of thing that takes a decade to build and can't be acquired by capturing an example, measuring its components, and issuing a production order. There is one final detail the Packard story offers that is easy to miss. When Rolls-Royce engineers stripped down the first engine from the Packard production line, they expected the acceptable but not ideal consistency of a scaled manufacturing process encountering a complex precision product for the first time. What they found was that Packard's tolerance consistency was better than their own. Rolls-Royce's hand-fitting culture had produced engines of potentially very high individual quality, but with meaningful variation between units. Packard's standardized approach had produced something harder to achieve: identical precision across thousands of identical engines. Rolls-Royce subsequently adopted elements of Packard's manufacturing philosophy. The engine that began as a British private venture, transferred to an American automotive company, came back across the Atlantic, having taught its inventors something about their own process. Britain and America, working together, produced approximately 150,000 Merlin engines before production ceased in 1950. Of those, roughly 55,000 were built in Detroit, representing about 37% of total output. The same engine, the same drawings. Two countries, one industrial ecosystem, built deliberately on both sides of the Atlantic at enormous cost. Germany had the blueprints. Britain and America had everything else. And the everything else, it turns out, was the engine. Subscribe if you'd like more stories like this one.